Does anybody have questions about homeworks that we've attempted or just want to talk some more about or anything in general? Go ahead, Claire.
Can you just give an example of like a problem where you get the domain
So like one of 5 through 10?
Yeah.
Okay, does anybody have any particular between 5 through 10 that they'd like to talk more about? I'd be happy to pick one if nobody does, but figure I could kill 2 birds, 1 stone. Okay.
Just not number 8.
Not number 8. Okay. Well, let's do 9 then. That seems like a good one. So f of x equals the square root of x minus 1. So the first thing I'll do is look at the implied domain. In this problem, since there's no context, it's not part of a story problem, x and y don't represent like real world objects, we can just assume the domain is all real numbers. To find the relevant domain, what I'm going to look at are the operations involved in the function. So in this function, I have subtraction and I have square roots. So I know if I subtract 2 real numbers, I will always get an answer, right? I know any subtraction always works. But square rooting doesn't, right? We can only square root some numbers. What numbers can't we take the square root of? Negatives. So what I'm going to do is I'm going to take everything that's underneath the square root and say that it cannot be negative. Or in other words, it has to be greater than or equal to 0. I can then solve this inequality. So I'll add 1 to both sides. And then I'll write this inequality as an interval. So if I think about what this inequality means, x is greater than or equal to 1. This inequality would include 1 and then everything bigger than it. So the smallest number in this interval would be 1. That will be my lower bound. And the biggest number in this interval, well, there is no biggest number because it goes on forever, would be then positive infinity. That will be the upper bound. Now, I know all the infinities get a parenthesis. And because if I look at my inequality, 1 is greater than or equal to 1. Since 1 satisfies that inequality, I know it should get a bracket. So there is a relevant domain. Is that okay, Claire? And when I ask for to do this algebraically, this is the kind of work that I would like to see, right? Is show me that you wrote down what the implied domain is, write down any work you did to get the relevant domain, and then write your interval. Is that okay? Leo?
Since it's a square root,
Depends on what we're square rooting. Right? So, first things first, if it was just a square root, it would be 0 to positive infinity, because you'd have things like 0.1 or 0.2. Those are all fine to take the square root of. You can still have decimals. But let's say that instead, we have the square root of 5 minus 3x or something. So the same thing, the implied domain is still all real numbers. And just like before, the parts under the square root can't be negative. So we'll solve this inequality for x. Ooh, oh my goodness, I wrote down totally the wrong thing. 5 minus 3x. Thank you. Okay. So we'll subtract 5 from both sides. Everybody good? Then we'll divide both sides by -3. What do I have to be careful about when I divide by a negative, though? Yeah, that inequality symbol is going to change directions. And that negative divide by negative is just positive. So here I have x is less than or equal to 5/3. So again, if I think about what that is, that's 5/3 and then everything's smaller, right? So the smallest number here, well, there isn't one because it goes on getting smaller forever. So that's going to be -infinity. And the biggest number here is 5/3 because it goes all the way up to 5/3, right? That's the biggest number. That's my upper bound. The infinity always gets a parenthesis. And the because 5/3 is less than or equal to 5/3, that would get a bracket. So it really just matters like what the stuff is underneath the radical as to what that domain is going to look like, right? So can put a bunch of different stuff under it, you get a completely different looking domain. Claire, does that feel okay?
Can you do number 12 also?
Sure. So notice the directions on 12 don't ask you to do this algebraically. They just ask to find the range. So you can do this just by like typing this into your calculator and looking at a picture. So if you looked at the calculator, this is kind of the picture that you'd get. If I look at this, this is the lowest point on my graph, right? If I looked at the tick marks, appears that that would be the 0.32. I can confirm that because if I plugged like 3 in for x, 3 minus 3 is 0, the square root is 0, 0, 0 plus 2 is 2, right? So I can confirm that, okay, what I read from the graph is indeed what it is. And the highest point on this graph is, well, there isn't one because I have an arrow that's going up and to the right. Everybody feel okay with that? So my range then, my lower bound is 2. That's the lowest y coordinate. Everybody agree with that? And the upper bound is positive infinity because you could think of this point since it's going to the right, it's going towards positive infinity in the x direction. And because it's also going up, it's going to like positive infinity in the y direction. Is everybody okay there? So I know the infinity always gets a parenthesis. And because I actually have a point whose y coordinate is 2, I know the 2 gets a bracket. And I'm all done. Okay? I didn't ask you to do it algebraically, so you don't have to do it that way. You can just kind of look at the picture and interpret what you see. Claire?
Would there ever be a problem like this that you would put bracket around that?
Sure. Do you want to see an example? Okay. So I'm going to refer to an example from last year. So let's say we have y equals 2 to the x plus 1 minus 3. So this is an exponential function, right? You guys vaguely remember talking about those last year. So one of the special attributes of all exponential functions is they have a horizontal asymptote. And that horizontal asymptote is always like y equals k. So for this one, the lowest point is here. And so that's going to be going towards negative infinity. And it's going to the y-coordinate, -3, right? But is it ever actually going to get to -3? No, because we know that that's a horizontal asymptote. The graphs will get close to it, but never cross it. So here I'm going to go -3 to positive infinity as my range. Oops. The infinity gets a parenthesis because it's an infinity. The -3 is going to get a parenthesis because there is no point on my curve that actually has the y-coordinate -3. That's the asymptote. It's never actually going to get there. It'll get real close, like -2.9999999, as many nines as you want to list, but it won't get all the way to -3. So there's an example of something we've seen before where like the lower bound or upper bound for a range might be a parenthesis rather than a bracket. And that's what you're asking for, right? Okay. Again, I'm going to try always to give you, when you ask for examples like that, to give you something you've seen before. Ideally, right? Whenever possible. Jeremy. 10? Sure. So this is h of x is 1, or x minus 1 over square root x. So again, the implied domain here is just all real numbers because there's no context given to this problem. To find the relevant domain, then I need to look at the operations involved. I see subtraction, I see division, and I see square roots. Now, subtraction doesn't cause any problems because you can subtract any two real numbers and always get an answer. Division, though, can cause a problem. So I know when I'm doing division, whatever the denominator is cannot equal 0. And I know square roots can cause a problem because anything I take the square root of has to be non-negative. Okay with that? Okay. Let's solve square root of x not equal to 0 first. How do I get rid of a square root? Square both sides, right? So the squared cancels the square root, and 0 squared is still 0. And I don't have to do anything for x is greater than 0, or greater than or equal to 0, because it's already the x is by itself. So far, so good. Now, if I look at these, I have x cannot equal 0, I have x is greater than or equal to 0. Let's combine these into a single thing. If x can't be 0, can it really be greater than or equal to 0? No, it just can only be greater than 0. So that's the inequality I have. So let's write our domain from that. X is greater than 0. Well, that's numbers like 0, 1, 2, 3, 4, 5. So we're starting at 0, and we're counting up as big as we want. So 0 is our lower bound, and positive infinity is the upper bound. The infinities always get a parenthesis. And because 0 is not greater than 0, the 0 gets a parenthesis. Does that feel okay? In general, Jeremy, if you have something like 1 over square root of stuff, instead of treating that as two separate things, you can just say stuff is greater than 0, rather than greater than equal to 0, and then not equal to 0. If it's something set up like that, you can just go straight to the greater than 0. Is that okay? Everybody else? And you can see why I'm skipping. I can skip straight to that. as long as it's kind of in that format. And maybe we don't even, I shouldn't be so specific. We'll just say other stuff on top. Right? You can have whatever's on top, it doesn't really matter. Any kind of gobbledygook you want. But if you have a square root over everything in the denominator, to find the domain, you can just take whatever's under the square root then and set it greater than 0, because it's also in the denominator. You know what I mean? Okay. What else, guys? These are good questions. I like kind of going off and doing some of these tangential, like what if we had this, or like could it ever do this? I think those are all important questions that you guys, shows that you're really thinking hard about what's going on and like looking for the next step and what else could happen. And, you know, I think that's really good. And I'm happy to do those kinds of things during these sorts of times. Claire?
Can you give an example where the implied domain would just be negative?
Yeah. So it would have to be like part of something with context, right? So let's say that f of x equals 2x plus 5, where f of x is the cost of something, and x is the number of people in your group or whatever, like your cost of a, you know, like let's say entrance fee or something. Okay with that? So since x is representing people, what kinds of numbers can represent people? Whole numbers, right? And even more specifically than that, what kind of whole numbers? I would say non-negative. I think 0 would be okay also, but whatever. So the domain there would just be like non-negative, or you could say positive. I wasn't specific enough here to, like, why 0 would be, like, would you really have a group of 0 people and stuff to pay money to go do this thing? That doesn't really make a lot of sense, but whatever. And I would just describe this in words, because since this is not a continuous set, like there's gaps in between the whole numbers, we can't use interval notation to describe this, and words would be fine in this kind of an instance. Everybody okay there? So that would be your implied domain is now all of a sudden not all real numbers. Does that feel okay, Claire? So you'd have to add some kind of like meaning to the variables, or be told straight out like, hey, your implied domain is, you know, something else. But the you need like some reason for the implied domain to, you know, to like be more restrictive, and it would come from, you know, like a real, you know, like attaching some meaning to the variable names. So unless you see a bunch of words with the problem, the implied is just going to be all real numbers, is what it basically comes down to, right? And even if there's a bunch of words, the implied domain could still be all real numbers, right? Okay. You need an example of that? No? Okay. Anybody else with questions on things? Okay, well, let's move on to the next thing. So if you guys, last time where we left off is we had talked about intervals of increasing and decreasing, and maximums and minimums. Today we're going to talk about another attribute of functions called symmetry. So there's three major types of symmetry that we'll talk about in this class. So the first type is called symmetry with respect to the x-axis. Now I like to abbreviate with respect to just as WRT. You're not required to do that. Same abbreviation, it's fairly common in the math world, and you're welcome to use that abbreviation if you'd like, but you are not required to. So what symmetric with respect to the x-axis is saying is that if I take the part that's like above the x-axis and I reflect it across to the part that's below the x-axis, they should lie like right on top of each other. That basically you have like a mirror image of the function if you're looking at the x-axis as your mirror, as your reflecting pond or whatever. Is that okay with that idea? Visually what we're looking at? Again, I haven't talked about any computation, just kind of a visual. So what that implies, that visual, is that if I have the point AB, I also have to have the point A negative B. Right? So if I have a point that's above the x-axis, I have to have that same point basically reflected across the x-axis, right below it. Is that okay? Or even more generally, what we're saying is that f of x is equal to negative f of x. Right? Because f of a is b and also negative b. That's all we're kind of saying there with our example. What do you notice about graphs with this kind of symmetry? Are they functions?
No.
Why not?
Vertical line test.
They fail a vertical line test. As a result, do you think we're going to see a lot of things that have this kind of symmetry? Probably not. Not until we go to second semester and we talk about a new way to define graphs like this that are still a kind of function. But for right now, we won't see a lot of stuff that has that kind of symmetry. The next one is things that have symmetry with respect to the y-axis. And again, WRT is just me abbreviating the phrase with respect to. You don't have to use that abbreviation also, but it's there if you'd like to use it. So again, when we say symmetry with respect to the y-axis, that means if I take the half of the graph that's on the right side of the y-axis and I reflect it across the y-axis, it should be identical to what's on the left-hand side of the y-axis. Again, imagine there's a mirror and that mirror is the y-axis. The one side should just be identical reflection of the other, right? Or, more generally, if I have the point AB, I'd also have to have the point negative AB. b. Or even more general than that, we would say that f of negative x is equal to f of x, which is what we're observing here, right? F of negative a is b, and f of positive a is also b. So we give these kinds of functions a special name beyond even symmetry with respect to the y-axis. We call these functions even functions. The next one is 180-degree point symmetry with respect to the origin. I'm going to abbreviate the word point as PT. And then I still use that WRT for with respect to. So what this 180-degree point symmetry with respect to the origin is, since it says with respect to the origin, it means that, like, if we have some point here, maybe I'll call that AB, and I pretend I tie an imaginary rope from that point AB to the origin, and I then rotate that point 180 degrees. It would land back on my curve. That's kind of what you have to imagine. It's a little bit tricky to imagine that with your mind's eye, but if you just kind of close your eye, imagine having a point here. It's like tied to the origin, so like it's just going to spin in a circle when you spin it, right? So you do like half of a circle, and you land any point you pick, and you do that, you land back on the curve on the other side. So in general, what this means is that if AB is a point on our curve, so is negative A, negative B. Or even more generally, f of negative x is equal to negative f of x. And these functions we give an extra special name to. We call functions that have this type of symmetry odd functions. So if we talk about a function being even or odd, we're talking about it having, one of these two types of symmetry. Doesn't have anything in particular to do with the numbers involved. It has to do with the type of symmetry the function has. Okay? So let's do some examples now. So we've seen the three types of symmetries. I would hope that if you saw a picture, you could pick out the proper type of symmetry. And if I ask you to prove a function has a certain type of symmetry, you could do the algebraic manipulation that we're about to kind of talk about and go through. Okay? So let's do some examples here. We're going to prove that the function is even, odd, or neither. So when we say prove here, it's not going to be like a 2-column geometry proof. It's going to be more like when we prove that two functions were inverses last year in our Algebra 2 course, where you do that like function composition to show that like you get x. The same kind of thing here, but instead what we're going to be doing is we're going to find f of negative x, since our definition of odd and even each start with f of negative x. And then if it's even, we'll see that we get f of x. If it's odd, we would have gotten negative f of x. And if it's neither, we'll get something else. So the nice part about this proof is that whether it's odd or even, which we don't know at the start, we'll begin the same way by computing f of negative x. So remember, when we write something like f of whatever, what that tells us is we're going to plug that whatever in place of all the x's in our function, right? If this was f of 2, we'd write 2 to the 4th plus 1. Everybody agree? Since we've written f of negative x, we're going to write negative x to the 4th plus 1. Now, if I have negative x to the 4th, that really means negative x times negative x times negative x times negative x. Everybody agree with that? If I multiply 4 negatives together, what do I get? Is it positive or negative? It's positive, right? And if I multiply 4 x's together, what do I get? X to the 4th, right? So negative x to the 4th is just x to the 4th. And then I still have that plus 1 at the end. Now let's compare this to the original. They're identical. Everybody agree? So I know that this is just f of x. And what does that tell me? Good, that this was an even function. So in general, we're going to compute f of negative x, simplify, compare that to the original. If it's the same, we're done, it's even. If it's not, we'll then check to see if it's odd. If it's not, then it's neither, and we're done. Let's do another one. Okay? So far, not so bad. The speed okay? I'm not going too fast? You guys can always tell me if I'm going too fast, or if there's something you're not sure you understand, or we need to talk about it some more, or you just need to hear it again. These are all okay things to ask. Just interrupt. Again, I'm trying to do my best and make sure that you guys understand things. And if there's something that I can do to help make that go a little bit better, or if we need a minute to process something or whatever, just let me know. Okay, so this one I have g of x equals 2x to the 3rd plus 3. We'll start it just like the other one by doing g of negative x. And just like the previous one, what does g of negative x mean? It means I'm going to plug negative x in for x in all the places Everybody good with what I did there? Okay. So let's simplify now. Negative x to the 3rd. Again, we do exponents first, right? So negative x to the third is negative x times negative x times negative x. 3 negatives is negative. X times x times x is x to the third. So I have 2 times negative x to the third, which is negative 2 x to the third. Everybody good with that? 3 times negative x is?
So 3 times negative x?
Yeah. 3 times negative x is?
3x.
Negative 3x.
Oh, right.
Everybody's good there? Okay. So I've done with my simplifying. Let's compare this to the original. Are those the same? No. So what does that tell me? It's not even. So let's keep going then. If it's odd, let's say to check if it's odd, I'm going to factor a negative sign off. So when I factor a negative sign out, the signs are going to flip. So the negative 2x cubed becomes positive, and the negative 3x becomes positive. Is everybody okay there? So if I look at just the part in parentheses, let's use a different color, and compared to the original, are those the same?
No. Well, oh, yeah. Right.
Yep, if I look at just the part in parentheses. So what that's saying is if I take the negative sign that wasn't in the parentheses and replace the stuff in the parentheses with g of x, that's still the same thing, right? I hung on to this negative sign, and then this is still the same as the stuff in green, right? So if I look at the beginning and end now, what do I have? G of negative x is equal to negative g of x. What can I say? It's odd. So again, I start with like f of negative x. I do that composition. I simplify. I check if my simplified answer is the original, and if it is, it's even. If it's not, I factor a negative sign off and see if the stuff inside my parentheses is the original. If it is, it's odd, and I'm done. If it's not, well, then it's neither. It would have been not odd and not even. Let's do another. So we'll start with h of negative x. That tells me to plug the negative x in place for all of my x's. Everybody good there? Okay, so let's simplify. Negative x times negative x is positive x squared. So the first one is 4x squared. Negative 3 times negative x is
that 3x?
positive 3x. And then the plus 9 is just stays the same. Everybody so far so good? I'm going to compare this to the original. Are they the same? No. One of the signs is different. Oops, so I know that this is not even. Everybody follow that? Okay, to check if it's odd, we factor out a negative sign. When we do that, all of the signs swap, so positive 4x squared becomes negative, positive 3 becomes negative, and positive 9 becomes negative. But we still have that negative sign out front, right? So I'm going to compare now the stuff inside the parentheses to the original. Are those the same?
No.
Nope. Some of the signs are different. So this is not negative h of x. So we can conclude it's not odd. Since it's not odd and it's not even, what does it then have to be? Neither. Are we able to follow the reasoning here? Joe?
So whenever you start one of these problems, you always do h, f, or g, whatever they give you, the letter or variable, times negative x.
You'd say of negative x.
Of negative
Yep.
x.
Because it's not multiplication that we're doing.
Yeah.
But yes.
Okay.
Yes.
Awesome.
I assumed that. I just wanted to make clear for everybody else that wasn't living inside your head.
Yeah.
You know what I mean?
Yeah.
Good. Do you guys want to, if I write one down, you want to give it a shot and then we'll go through it as a group?
Yeah.
Okay. Let's do that. A, B, C, D, E, F, G, H. I guess I is the next one. So I'll give you guys a couple of minutes to work on this one. We'll go over it as a group in another, after, 3-4 minutes or whatever, give you guys a chance to grind on this one a little bit, give it a try on your own, and we'll go through it together. So look at the previous examples, see how far you can get. There's no pressure to get it right or wrong, but trying, even if you're not really sure what to do, helps to kind of cement the learning. So we've been talking about this for a minute. Oh.
We don't have school this Friday and next Monday, right?
Correct. Yeah, even if you look at the oh, I didn't update my agenda here for your class, huh? It's bad on me. I'll get it. Don't worry, something else to do. There, now I fixed that. Ha ha. Yes, sir. Of course. What do you think? You guys ready to go through this thing? All right, let's do it. So I of negative x, 7x, or 7 negative x cubed plus 1 over negative x minus 5 times negative x. Everybody good with that? Okay. Negative x to the third was just going to be negative x to the third, so that's going to be negative 7x to the third. 1 over negative x is the same thing as like negative 1 over positive x, right? So I'm going to move that negative sign just out front. And then negative 5 times negative x is positive 5x. Everybody agree? Okay. Well, clearly this is not I of x, so it's not even. Right? All right. Well, let's see what happens if I factor off that negative sign. So negative 7x cubed becomes positive. Negative 1 over x becomes positive. And positive 5x becomes negative. That is identical. So the negative sign comes with me. And that's equal to I of x. Oh, that's not how I've been writing it. Just do this. So it's odd. We feel okay with that? In general, for a lot of these, you can look at the function and tell whether it's going to be odd, even, or neither. Do you want to know? Did anybody figure out the trick by now? So if you have a polynomial function, like we had for a, b, c, right? Each one of those functions are polynomials. Everybody agree with that? You can figure out whether they're going to be odd, even, or neither just by looking at the degrees. So in the first one, you have a degree 4 and a degree 0. Because the degrees are all even, I know this will be an even function. In the next one, we have a degree 3 and a degree 1. Since those are all odd, I know it'll be odd. And in the last one, I have a degree 2, a degree 1, and a degree 0. Because they're not all odd or even, I know it'll be neither. So that's nice, right? Like you can look at a lot of these and just tell right from jump whether they'll be odd or even. Just by looking at what the exponents are on the monomials. That's pretty cool. And I think this is as far as I really wanted to get today. Would you rather cram some more in and be able to take a break later? Or take your break now and just to have like a full day on Wednesday.
Probably a full day Wednesday. Can we do homework right now?
You want to chill for the last 10, 15 minutes? Yeah, that's cool. There wasn't much to add. So we'd have 19 to 22 was the new stuff from this section.